Time has always been treated as a basic part of reality, something that simply exists and moves forward. But recent work in theoretical physics is challenging that assumption. New research in quantum gravity, space-time theory, and quantum information science is pointing toward a surprising idea. Time may not be a fundamental feature of the universe at all. Instead, it may emerge from deeper physical processes that govern matter, energy, and information. This isn't speculation anymore. It's becoming a serious scientific discussion driven by real mathematical models and modern theory. In this video, we will explore what scientists mean by a timeless universe, how physics is redefining time, and what this could mean for our understanding of reality. Let's get started. The challenge to time begins with one of the central problems in physics, the failure to unify quantum mechanics and general relativity into a single coherent theory. Quantum mechanics governs microscopic systems, particles, fields, and fundamental interactions. General relativity governs gravity, space-time, and the large-scale structure of the universe. Both theories are experimentally verified and extraordinarily successful, yet they define time in fundamentally different ways. In quantum mechanics, time is a background parameter. It does not interact with matter or energy. It does not curve, stretch, or respond to gravity. It simply labels change mathematically. Time exists outside the system being described. In general relativity, time is physical. It is part of space-time itself. Gravity is not treated as a force, but as the curvature of space-time, meaning time is directly shaped by mass and energy. Time is dynamic and embedded in the structure of reality. When physicists attempted to merge these two frameworks into a single quantum description of the universe, the result was not a simple combination of models. In 1967, John Wheeler and Bryce DeWitt developed an equation intended to describe the quantum state of the entire universe. In this equation, time does not appear. This was not a conceptual choice. It was a mathematical result. When the universe is treated as a closed quantum system, time disappears from the fundamental description. This created a serious implication. If the most fundamental equations describing reality contain no time variable, then time cannot be fundamental in the same way space, energy, or quantum fields are. Modern quantum gravity research has continued to reinforce this tension. Some theories treat time as emergent, a property that arises from deeper physical processes. Others treat time as relational, meaning it exists only through interactions between systems. Some models describe time as discrete rather than continuous. Others remove it entirely from fundamental structure. At the same time, physics has never directly measured time as a physical entity. Experiments measure processes, oscillations, decay, energy transitions, entropy changes, and motion. Time itself is inferred from change. It is not observed as a substance, field, or force. Taken together, these developments point toward a consistent conclusion. Time may not be something the universe contains. It may be something that arises from how physical systems behave and interact. If time is not fundamental, physics must explain two things: why time appears real and why it seems to move in one direction. Most fundamental equations in physics are time-symmetric. They work the same forward and backward in time. Nothing in the equations distinguishes past from future. Physics itself does not encode a natural temporal direction, yet experience is clearly directional. Memory points backward, entropy increases, systems decay, order moves toward disorder, causes precede effects. This asymmetry defines what we perceive as the flow of time. Thermodynamics explains part of this through entropy. Entropy increases statistically, producing an apparent arrow of time. But entropy does not define time itself. It describes probability distributions in physical systems. It explains direction, not existence. Quantum physics introduces a deeper framework. In quantum entanglement, systems form correlations that do not depend on spatial distance or classical causality. These correlations create structured relationships that exist independently of classical time ordering. Some modern theories propose that time emerges from quantum correlations. In these models, temporal order arises from patterns of entanglement and information exchange between systems, not from a background time dimension. Time, in this framework, is not a container where events happen. It is a relational structure generated by interactions. Other theoretical approaches support similar conclusions. Loop quantum gravity treats spacetime as emerging from quantum geometry. Holographic theories describe spacetime as a projection from lower dimensional information systems. Information-based models treat reality as networks of relations rather than objects evolving in time. This reframes time as an emergent property. Similar to temperature. Temperature feels real, but it does not exist at the particle level. It emerges from collective motion. In the same way, time may emerge from collective quantum behavior. If this is correct, then time is not a fundamental feature of reality. It is a derived phenomenon, real in experience, but not basic in structure. If time is emergent rather than fundamental, the implications extend far beyond physics. Causality becomes relational rather than absolute. Concepts like before and after may only apply at macroscopic scales. At fundamental levels, reality may be structured without sequence. Cosmology would also be reframed. The Big Bang would not represent the beginning of time itself, but a boundary condition within a deeper atemporal system. The universe would not evolve in time. Observers within it would experience time as an internal phenomenon generated by physical structure. Change would no longer be a universal property of reality, but a local property of complex systems. While direct experimental verification of timeless physics remains difficult, indirect evidence continues to accumulate through quantum correlations, entanglement modeling, space-time geometry research, and entropy-based theories. Future research aims to build testable models where time emerges naturally, explain the arrow of time without assuming fundamental temporal flow, link entropy, information, and entanglement into unified frameworks, derive observable predictions from quantum gravity theories. This represents a structural shift in physics. The question is no longer whether time behaves strangely. The question is whether time exists in the way we assume it does. Time may not be a fundamental feature of reality, but an emergent result of deeper physical processes. Physics is beginning to treat time as a product of structure, not the structure itself. Understanding that shift may change how we define reality itself.